In this video, I'll show you exactly how to simulate welding in Abaqus using birth and death technique step by step. First, I'll explain the overall strategy behind the method and I'll walk you through a complete example so you can see how it works in practice. For your convenience, the files are also included, so check the description down below to download the files. Let's get started. What we have here is a V-groove welding model and it is a full model, but don't worry, it can also be applied on a symmetry model. I'll show you later. So instead of having one big part like this, we need to make it into smaller chunks, just like this one. So this is the first thing we need to do, and the rule of thumb is the more part we have, the more accurate the simulation be. Next, we need to go to the step and defining the step time. So if we have one big part, the step time would be the same as the welding time. But since we have 4 smaller chunks, the welding time must be divided by 4. So if we go here, let's say we have a welding time of 4 seconds. We need to have 4 different steps. Each of them must be 1. So 4 divided by 4 is 1. Additionally, we need to have 1 step death. So we put all elements in deactivated mode and we reactivate them step by step. And for sure, we're going to have a cooling step. Next, we need to go to the mesh. Pay attention because this is the most crucial part of the simulation. And if you mess it up, your model would be wrong. You need to create a bunch of sets here to define the path. So we go to the tools, set and manager, and we see we have like part 1, part 2, part 3, part 4, and if I replace selected here, you would see you have only these elements in the set. There are 2 reasons behind this. First of all, we can calculate the volume of each part. Then we need to divide the thermal load by each volume in order to have the volumetric loading for each part. The second one is to reactivate them. And last but not least, we need to go to the interaction and we create a bunch of interactions. So first of all, we need to create one interaction to deactivate all these elements. Then we need to reactivate them one by one. As you see, like this one, this is in the reactivated steps and the region type is elements. So we reactivate all of these elements so that you can have a smooth transition. You can also save the consumption of CPU by creating a symmetry model. So here we have the symmetry. As you see, it is only half of the groove and we have more parts here. It's the same scenario. We have 8 parts here. Then if we go to the step, we have 8 steps. So this is more accurate than the previous one. The step time is 4 seconds, but it's divided by 8. So each step would be 0.5. Then in the interaction, we have 9 interactions. The first one is to deactivate all the elements. Then we reactivate them one by one. And the elements are in the set. So if we go to mesh to check it out, and we have to click the part. Then if we go to the set manager, we have part 1, 2, and it goes all the way down to the part 8. Now let's begin the practical example. Before we begin, I want to ask you a favor. If you enjoyed this video so far, please leave a comment for me down below. And if you want to support the channel, go to the video and here click on the dots and click the thanks button. Or you can join the channel to support. You can also click on the pinned comment to buy me a coffee. Thank you very much. Okay, we start our tutorial with creating the part. Create part here. This name is part 1. Should be 0.2 because we're going to create that in metric. And it's okay. Now I want to create a rectangle. The first point is 0 and 0. And the next one is 0.05 and 0.0025. Now I have my part. By clicking on scroll button, I'm going to enter the depth here. It's 0.025. And okay, now I have my part here. Now we need to create the bevel here. So I go to the partition face sketch, select this face, and scroll button, then vertical right, I choose this one. Now this pops out. I create a line like this, then I need to assign the angle. The angle must be 30. Now here is the bevel here. In this tutorial we're going to have a symmetry model, so this is half of the model, right? We need to create 2 more points. Here it is, because I want to create another zone. So this one should be 0.0042 and this one must be 0.0056. Scroll button once more, and this is going to be my other zone. By left click and hold on this one, I need to select partition cell and sweep. So I select this one, and by holding shift and this one, done. Sweep along edge, and I select this edge, and as you see, I have my partitions created. This is the weld line, and the other one is heat affected zone maybe, and this is the base metal. Okay, now we need to create more partition. Left click and hold on this one, and partition cell define cutting plane. I select this cell and 3 point. I first select this point, and as you see, a partition is created. Now I want to do it for this one and this one to see how it goes. 3 points, this one, and here. Now I'm going to make these 4 into halves in order to have 8 partitions here. Okay, this one, 3 point, here, and here. The last one is here, 3 points. And we have our weld line here divided into 8 partitions. Let's go to the property. Here we need to create the material properties. The material is steel. I have an Excel sheet here containing everything. So I copy this one, general density, and check this use temperature dependent data, and I paste it here. Now let's go for the next one. We can have conductivity here, thermal, conductivity, temperature dependent data, and we have the conductivity here. Specific heat is the next one, thermal and specific heat. That's all for now. The other things like expansions, or for instance here the elastic modulus or yield stress, are for residual stress analysis. We don't need them right now, and surface film coefficient and emissivity can be used in the next modules, interactions. And we hit OK. Okay, now create a section, solid homogeneous, steel, OK. And now we assign this to here. I uncheck this one, done, and OK. Now let's go to the mesh. This time I want to seed the model. Okay, we start from the base metal part. So I select seed edges. I select this one by holding shift and this one, and I can hold shift and select these other 2. And done. This should be single bias. And as you see, the arrows are facing toward here, which is totally fine. I would like to put the minimum on 0.0005 and the maximum can be 0.001. And we hit OK. Now you see it's entered. Now it's time to say this one by holding shift and this one. We can rotate the model to select these 2. Hold shift, select these 2, and we jump back here, done. And as you see, the arrows are facing the other way. We need to flip them. Here, flip bias, we select this one, this one, and this one, and done. Now as you see, the arrows are facing the other way, which is totally fine. Okay, it was for the previous one. I copy and paste it here because the minimum of this one must be the maximum of this one. This can be on 0.003, and okay, now we need to define that for the weld part. I select this one, this one, this one, this one, and every parallel line in the welding by holding shift. If you select something unexpectedly, hold control and click on it, it can disappear. Alright, I selected everything. This time you don't need the bias, but you need to enter the size 0.003, and as you see here we have the mesh. Now I need to select these lines, select them carefully, and the lines parallel to them, I mean this one and this one. Now everything is selected, done. This time this should be 0.001, and okay, now it's applied. The last thing to do is to select these lines, need to select this one, need to select this one right here. You also need to select these lines. This is right, so it's better to rotate it. This one and this one, right? We selected every line here, done. And this time I put it on by number, and I want to have 5 elements in this direction. Now the last thing is to select these lines here, yep, all of them, and it needs to be 0.0003. Now it looks good. Let's mesh the model to see how it goes. Yeah, this is what we wanted. Now it's time to create some sets. So I put this one on cells, select this one, hold shift, and select all the weld line, and let's say replace selected, and from tools, set, manager, I create all weld and put this one on element, continue, select all of them, and done. Now we have all weld made of elements. Now we need to create more sets. Okay, put this one on cell, this one, this is the first one, and replace selected, tools, set, manager, create, for instance, part 1, make it of element, select whole model, and done. Now it's time to do the next one. So this is the first cell, second cell, and you need to replace selected, create part 2 element, continue, select it, done. Now you have to do it for all of them. Now it's the third one, done. Now we're done with the mesh and sets. Let's go to assembly first, create the assembly, that's okay. Now let's go to the step to create the steps. The step must be heat transfer initial. The first one is the step death, because we want to deactivate all of the elements, then reactivate them by the passage of time. So I put 1 on this one. The time period doesn't matter, I put a very small value. This one 1000, 1e minus 2, 1e minus 20, 0.05, and this one should be 350. So imagine the welding speed is 12.5 millimeter per second and the whole part is 50 millimeters. The whole welding time must be 4 seconds, and as we have 8 parts, each part must be 0.5. So I'm going to create the steps. Here it should be step 1 comes after death and continue. The time must be 0.5. This is 1e minus 2, 1e minus 20, and this should be the half of this time, so it is 0.25. This one is 1000 and the maximum allowable temperature is 350. Now we need to create 8 steps, totally the same, 0.5, 1000, 1e minus 2, 1e minus 20, 0.25, 350. Okay. Yep, now you need to create a cooling step. So this is cooling. Let's put the value of 2000 for instance, 1000 for this one, 1e minus 2, 1e minus 20, put this one on 200 and 350, and this is okay. Now we need to go to the field output manager, and here is created here. We don't need the heat flux or this one, we only need the nodal temperature, and okay. Now the step is done. Let's go to the interaction. Now we need to create multiple interactions, so I create this interaction here, and it should be step death, must be model change, continue, and it says select the region type can be element, and we can select it from set here. So we have all weld. We can also highlight this here, you don't see it here, continue, and this region must be deactivated in this step. So this is the first interaction to create. Now I need to reactivate all the elements. So interaction 2 comes in the step 1, model change, and this should be elements and must be reactivated in this step, and the region must be part 1, continue, and okay. Now as you see, it is created here, right? We need to do interaction 3, step 2, model change, elements, reactivate, and select part 2, and okay. Now the interactions are selected. If you double click on them, you can see and monitor them to see if it's okay or not. Plus you can make sure that the correct part is selected. Here step 6, part 6, and step 7, part 7, and this is part 8. Okay, now we need to create other interactions. You go to step death, select surface film condition, continue, select everywhere. You don't need to select the symmetry plane, so by holding control you can deselect here. Yeah, it's not selected here, and you rotate it, and you don't need to select this one. Okay, now I'd like to create a surface and name it surfaces, maybe. done, and the film coefficient can be selected using the property. So property reference, create interaction property from here, it should be film condition, continue. It is film coefficient, use temperature dependent data. Let's go here and find it, surface film coefficient, Control C and Control V. Now we select it here and sink temperature can be 25 and OK. As you see, the interaction is created. Now we need to create another one, which is surface radiation. Continue. So from here, from surfaces, you can select surfaces because it's the same. Put this one on 0.49 and ambient temperature is 25 and OK. Now as you see, the interactions are created. Now it's time to go to the load and boundary conditions. Now imagine in this case we want to calculate the heat input. The heat input is voltage times current times the efficiency eta over the travel speed. Imagine here we have 22 volts and 57 amperes, and the eta is 0.65, which is for the manual metal arc welding or sheet metal arc welding SMAW, and the speed is 12.5. In this case, the heat input would be 75.35 joule over millimeter, and as we are doing it in the symmetry model, it should be 32.67. But here we need to calculate the volumetric heat input. So I jump back to Abaqus, and I go to the mesh, put this one on cell, select one of these and replace selected. From here we can go to the query and mass properties. You select the mesh entities, you select here and down, and it gives you the volume, which is this one. Now if you divide that number by this one, it should be the load. Now jump back to Excel file. First we need to calculate the total power. The total power is heat input times the speed, which is 408.45 watt, and if we divide this number by the volume, it gives us the load. So the load must be 3.615 E10 watt over meter cube. This is how you can calculate the load for your simulations in any specific article you're working on. Right, now we go back to Abaqus to perform this. So we go to the load, replace all. Okay, now we need to create local coordinates here, 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 and so on to apply the load on them. Okay, now we select this one, create datum CSYS 3 point. It can be rectangular, and here is OK. Then we need to create the next one. Every time I hit the scroll button. Alright, now we created different local coordinates except for this one, and now we want to apply the load. Okay, now we need to create the load. It can be body heat flux, step 1, which is load 1. Okay, you select this one because we're going to apply the load on this one. Done. The distribution should be through the analytical field. So this is analytical field expression. Continue. Now if we go to the Excel file, I have the formula of the heat distribution here, and I can put it here. We also need to select the local system, so this must be our local system. Then hit OK. You select it here, and the load is 36 E10. Then hit OK. As you see here, we created the load, but it should be deactivated in the step 2, so we only need it for step 1. Now we need to do that for different steps. So step 2, select this guy. We need to create another analytical field, this one, but this time this should be here. Okay, analytical 2, 3, 0.6 E, 10, done. Then deactivate it for step 3. Now to make it more realistic, I think it's better for the ampere to be 100, 120 or something. So in this case it's better to change the loads to realistic values. I already calculated that, so I replace all these numbers for these realistic values. And that's it. We also need to create the predefined field, so the predefined field can be in the step depth. Continue, select everything, done. The magnitude can be 25. Yep, so it means from the beginning we have the temperature of 25 all over the material. And now we need to go to the mesh. We select everything, done. And this one should be heat transfer. Alright, now before submitting the job, we need to go to the model and here edit attributes of model 1. Absolute zero temperature must be negative 273.15 and the Stephen Boltzmann must be 5.669 E minus 8. We need to create a job, but before we submit a job, I want to ask you a favor. If you enjoyed this video so far, please share your feedback with me in the comments down below. It's totally free for you, but it motivates me to create videos like this. Okay, let's create a job. We name it welding distribution. Continue. Okay, now we can submit the job. Hit the yes. Okay, it takes a while. I'll continue after the job is completed. Now the job is completed. Let's go and take a quick look at the results. This is the nodal temperature. This should be, yeah, okay. Yeah, as you see here, we have a reasonable temperature. The flux is moving. Cool, let's stop it here. And I want to go to here and let's plot the time versus temperature. Okay, from XY data, ODB field output, continue, you go here from unique nodal temperature and you can select different points. Let's select here, hold shift here and this one and plot them. If you select them one by one and select edit, you can copy and paste these values in your Excel file. And let's go here and see if the root of the weld is melted. In this case, you need to go to the query probe values. You can use elemental or you can select nodal. So I select the node here and I select this one and it gives me the temperature, as you see here, is 728, meaning that it's not melted, so the parameters must be changed. But here we only wanted to show you as an educational purposes. And that's it. If you enjoyed this video, hit the subscribe button to see more videos like this. And if you want to learn residual stress in additive manufacturing, click on the video on the screen before it ends. Stay tuned.